Consider an 8x8 board. Let's place a knight, one of the chess pieces, in the top left corner of the board. The knight moves like an L shape. For instance, from this square, the knight can move to these squares. We will now number each square that the knight visits, starting with the square it is initially placed on, which will be numbered as 1. The knight can go to this square next, so we will number this square as 2. Next it can go here, so we will number this square as 3, and we will continue numbering the squares as the knight visits them. After 64 moves, the knight will have visited every square on the board, and will end up in this square. Now something interesting occurs. When we examine the sums of the numbers assigned to each square in each row, we find that the sum of the numbers in the first row is equal to 260. The sum of the numbers in the second row is also 260. In fact, the sum of the numbers in every row on the board is equal to 260. Similarly, the sum of the numbers in each column is also equal to 260. A square that exhibits this property, where the sums of all its rows and columns are equal, is known as magic square. To be precise, this specific magic square is known as Knight's Tour, which was initially presented by William Beverley in 1848. Magic squares can come in various sizes and forms. A collection of numbers arranged in a grid can be called a magic square if the sums of the numbers in each row, each column, and both main diagonals are equal. However, in the specific case of the Knight's Tour magic square, only the rows and columns have the same sum, while the diagonals have different sums. This variation is referred to as semi-magic square. The size of a magic square is determined by its order, which corresponds to the number of integers along one side of the square. It is usually denoted as n. Additionally, the constant sum obtained by adding the numbers in each row, column, and diagonal is referred to as magic constant. A magic square is considered normal if the numbers within the square are consecutive integers starting from 1. Magic constant for a normal magic square of order n can be calculated from this formula. That is a normal magic square of order 1, and there is only one possible way to construct it. A normal magic square of order 2 does not exist and cannot be constructed. For a normal magic square of order 3, there is only one distinct arrangement. Even if it is rotated by 90, 180, or 270 degrees, it is still counted as one unique configuration. Moving to a normal magic square of order 4. There are already 880 known ways to construct such a square. When it comes to a normal magic square of order 5, there are an extensive number of possibilities, specifically 275,305,224 ways to construct it. The precise number of ways to construct a normal magic square of order 6 is not yet known, but estimates suggest that it could be around 1.77 times 10 to the power of 19. Magic squares can be constructed using any set of numbers, but we can impose more constraints. For instance, a specific constraint could be using only prime numbers to create a magic square. By doing so, we can generate a magic square consisting exclusively of prime numbers, referred to as magic square of primes. That is a 3x3 magic square of primes with the smallest possible magic constant. When a magic square remains magic, even after the numbers are raised to a power, it is known as multi-magic square. A specific type of multi-magic square is the bi-magic square, where the numbers are squared. For example, consider an 8x8 magic square, with the magic sum of 260. When each number in this square is raised to the power of 2, a new magic square is formed with a magic constant of 11,180. Therefore, this magic square is classified as bi-magic square. It has been proven that constructing a bi-magic square of order 3 is impossible. And the same holds true for the fourth order. The smallest known bi-magic square is of order 6, which was created in 2006. This bi-magic square has a magic constant of 408, and when the numbers are squared, the magic constant becomes 36,826. While numerous bi-magic squares of orders greater than 6 exist, It remains uncertain whether a bimagic square of order 5 can be created. Its possibility has not been proven or disproven yet. Now consider a magic square of order 12, with a magic constant of 870. When the numbers in this square are squared, it remains a magic square with a magic constant of 83,810. Remarkably, if the numbers are raised to the power of 3, the square also remains magic with a magic constant of 9,082,800. This square is referred to as tri-magic square. It is the smallest known tri-magic square, as it has been proven that tri-magic squares of orders less than 12 do not exist. In addition to the traditional additive magic squares, there exists another type called multiplicative magic squares. These squares operate based on multiplication instead of addition. For instance, consider a multiplicative magic square with a constant product of 216. This means that when we multiply the numbers in any row, column or diagonal, the result is 216. This square is an additive magic square with the constant sum of 465. It also qualifies as a multiplicative magic square because it maintains a constant magic product. It is referred to as an additive multiplicative magic square because it has both the constant sum and product. It is also the smallest known additive multiplicative magic square. An anti-magic square is a configuration of numbers in which the sums of each row, column and diagonal form a sequence of consecutive integers rather than having a constant value as seen in traditional magic squares. The smallest anti-magic squares are of order 4. For instance, in this square, each row, column and diagonal has a specific sum. These sums create a sequence of consecutive integers. This row has a sum of 29. This column has a sum of 30, and this diagonal has a sum of 31. These sums continue in a sequential pattern as we move across the square, until we get to this row which has a sum of 38. In addition to magic squares, there exist other types of magical shapes. There are also magic triangles, where numbers are arranged along the sides of a triangle. Consider an example of a magic triangle with an order of 3. In this triangle, each side consists of 3 numbers. The sum of the numbers on each side is equal to 9. Magic hexagons introduce another shape that can possess magical properties. In these hexagons, numbers are arranged in a centered hexagonal pattern. Each row, regardless of direction, sums up to a constant value. Interestingly, only 2 normal magic hexagons exist. Normal magic hexagons are those constructed using consecutive integers starting from 1. The first normal magic hexagon is of order 1, which consists of only one value. The second normal magic hexagon is of order 3, where each row sums up to 38. While it is possible to create magic hexagons of different orders, they will not meet the condition of consisting of consecutive integers starting from 1. Another shape that exhibits magical properties is a star. In magic stars, numbers are placed on each vertex and intersection point. The sum of the 4 numbers on each line within the star is equal to the magic constant. The order of a star refers to the number of points it has. The smallest possible star consists of 5 points, but it is not possible to construct a 5-pointed magic star. The minimum order for a magic star is 6 points. A normal magic star of order n, which includes consecutive integers starting from 1, has a magic constant equal to 4n plus 2. For example, a normal magic star of order 6, also known as magic hexagram, has a constant sum of 26 on each line. Another shape that can possess magical properties is a circle. In a magic circle, numbers are arranged along a set of rings and diameters. The sum of the numbers on each ring and the sum of the numbers on each diameter within the circle are equal to the magic constant. Consider this magic circle consisting of 4 rings and 4 diameters. This circle is constructed using consecutive integers ranging from 1 to 32. The sum of numbers on each ring and each diameter is equal to 132. Magic shapes are not limited to 2 dimensions. They can also exist in higher dimensions. In the 3rd dimension, The equivalent of 2D square is a cube. A magic cube is characterized by having the sum of numbers on each row, each pillar, each column, and each of the 4 main space diagonals equal to the magic constant of the cube. A normal magic cube of order n, which has dimensions of n times n times n, is constructed using consecutive integers starting from 1 up to n cubed. The magic constant of such a cube is given by the formula n times n to the power of 3 plus 1 divided by 2. For instance, in this magic cube, every row, column, pillar, and diagonal has a sum of 42. The concept of magic shapes can be extended to dimensions even higher than 3. In these higher dimensions, cubes become hypercubes. The specific hypercube in the 4th dimension is known as Tesseract. Theoretically, it is possible to construct a magic tesseract. We can even calculate the magic constant for a normal magic tesseract of order n. It is equal to n times n to the power of 4 plus 1 divided by 2. However, visualizing the exact appearance of a magic tesseract is beyond our current comprehension, as it exists in a higher dimensional space that surpasses our imagination.